Good morning, guys. Hope you're doing well. We're going to go ahead and record the reactions lecture. This is not 111, so we're not doing equilibrium. We're doing chemical reactions. So I will go ahead and get prepped for that. I'm going to have to share my screen to be able to do so. So we'll share my screen, and then I will come back into PowerPoint and start my slideshow. So, like I said, we're going to be talking about chemical equations today. That's our goal, is to talk about what chemical equations are, how we do these things, and the balancing that goes on. Balanced equations are one of the biggest challenges in chemistry. If you can't balance an equation, everything else falls apart after that, because you can't do any of the calculations that we will eventually do without a balanced equation. So let's talk about that, how we get to a balanced equation. So we'll talk about chemical reactions and chemical equations. We'll talk about how to balance those. We'll do some practice for that. We'll talk about nuclear reactions, because this is the only time we talk about it. So we'll need to talk about some of the elementary particles that we deal with in nuclear reactions, and then practice balancing some nuclear reactions. Again, we're only going to talk about balancing nuclear reactions. We're not going to talk any more about them, but it is part of the balancing of equations that we need to do. So for the following mass/composition combinations, calculate the number of moles and the number of molecules. All right, so this is a review from last time. I'm going to go ahead and get my paper set up, and then I can show you what I'm doing. And let's write down some of the things that we have on this particular slide. So the first one we're going to do is 600 grams of NaCl. I want to know number of moles, number of molecules. I want to know 462 grams of PbSO4, and then 13.65 grams of Mg3PO4 So like I said, I'm going to go ahead and show you. Sorry, using a different computer today. I'm having to move some things around in ways I wasn't expecting. So here's my paper. Let's see if we can zoom in a bit. I think that's the best I'm going to be able to do. Okay, so we want to calculate the number of moles and the number of molecules. In order to calculate the number of moles, I need to have molecular weight. And then once I've gotten to moles, I can convert to number of molecules using Avogadro's number. So I'm going to set my move a couple of things around, which I didn't think I was going to have to do. Yay, fun! And I have a periodic table over here that I'm using for this. I'm expecting that you will have a periodic table with you that you can use while we're talking. I would recommend using the one that you're going to have on the test, because then you get used to using it and finding things on that particular table. In the beginning, I will show you the process of getting a molecular weight, how I go about doing that. I will eventually stop doing that, because I will expect that you will have figured out how to do it. So if we're going to talk about NaCl, we need the mass of Na. So 22.99 grams for Na. And then Cl, which is over here, 35.45. That means my total, if I have a calculator, 22.99 plus 35.45 gives me 58.44. grams, and that's for sodium chloride. So 1 molecule of sodium chloride is 58.44 AMU. 1 mole is 58.44 grams. So since I know that that's how many grams per mole, because that's how it's defined, I can take my 600 grams of NaCl. I can multiply, or actually divide by 58.44 grams in 1 mole of NaCl. My grams of NaCl cancel out, and that's going to leave me with an answer that I can deal with. And I'm going to go ahead and calculate that number and give you that answer. So 600 divide 58.44, and eventually I will have it set up so that I can show you the calculations that I'm doing. And I come out with 10.26694045. Now, I'm going to keep all of those digits. If I were going to report this particular number, I would report it as 10.27 moles. But I'm going to keep all those digits because I didn't want to use Avogadro's number. So I'm going to take and multiply this. So this guy then gets multiplied by 6.022 times 10 to the 23rd molecules per mole. And that'll give me an answer. So 6.022 second EE23, because that's what that needs to look like. We need to enter that in that way. And then we'll enter that, and that gives me 6.183 times 10 to the 24th. 4 sig figs, because that's what I had in both of my masses. And for now, we're going to use the number of sig figs in the masses. Okay. All right. So that's how many molecules I have and how many moles. I can do something almost exactly the same when we talk about the PbSO4. So I have to find Pb first. Where is my favorite dude? Pb is lead. He's 207.20. And again, that's grams per mole. Sulfur over here, 32.07. And oxygen is 15. No, it's listed as 16. Now I know that my 16, there have to be 4 of them for me to get my total. So I add 207.20 plus 32.07 plus 16 times 4. That gives me 303.27. I can then take 462 PbSO4. I divide that by the molecular weight that I just found, 303.27 grams per mole. And that's one of those calculations. I'm also going to set up the 6.022 times 10 to the 23rd to show you what that looks like, molecules per mole. Moles cancel, grams cancel. So that's how I would do the setup for the second one. So the first calculation to find the number of moles is just the 462 and dividing by the molecular weight. To get the number of molecules, I need to do this entire calculation. So I take my 462, I divide by the molecular weight that I calculated, and that gives me 1.523 moles. Okay. I then multiply that times Avogadro's number, 6.022 times 10 to the 23rd, and that gives me an answer of 9.17 3 times 10 to the 23rd molecules. Okay? So 1.523 moles. And again, I only use that there. So the rounding that I've done, I don't do on my calculator. I use all of the digits that I have on my calculator. Make sure you do that, otherwise you run into rounding errors. Now let's calculate our mass for Mg3PO4. And I'm actually going to use a little bit of this space up here to do that. So Mg, P, and O. I have 3 times that, 2 times the phosphorus, and I have 8 times the oxygen, which is 16 grams per mole. So magnesium is 24.31. And phosphorus is 30.97. Now remember, the 3 is infinitely significant. So our answer is going to be 72.93 grams per mole. 2 times 30.97, and that's 61.94 grams per mole. And if I add all of that happy stuff together and put my answer over here, 72.93 plus 61.94 plus 128, it gives me 262.87 grams per mole. And again, since there were 2 sig figs past the decimal point for each of those numbers, which is part of the reason that I use this particular periodic table, because they're all that way, then my answer should have 2 decimal places as well. Addition and subtraction, we're concerned about the number of decimal places. So now I have my molecular weight for Mg3PO4 2. So then I can take 13.65 grams of Mg3PO4 2. I divide that by 262.87 grams per mole. And I'm going to write the answer here and then pull this like this to say I would take that and multiply it by 6.022 times 10 to the 23rd molecules per mole. And yes, my handwriting is awful. And that will give me my second answer that I'm looking for. So I take my mass, 13.65. I divide that by 262.87, and that gives me 0.05193 moles. I then multiply that by 6.022 times 10 to the 23rd, and I do that without having rounded like this. And that will give me 3.127 times 10 to the 22nd molecules. Okay, so I have now found all of those guys. So I found the number of moles and the number of molecules for all of these things. I took the mass that I was given, I divided by the molecular weight that I calculated, and then to get my final answer, I multiplied by the number of molecules per mole, and that's Avogadro's number. So that's how we get to that. Now, having said all of that, let's go back. There we go. And look at our questions again. So we're not done with all of our questions. We did the first 3. Now let's look at the next couple. So now we're going to be calculating percent composition. we're going to do that for NaCl, PbSO4, and Mg3, PO4, 2. Now I calculated the molecular weights for all of these previously. So I'm going to go back and look at my mass. So for NaCl, it was 58.44. For PbSO4, I calculated 303.27. That's this guy right here. Oh, sorry, I'm not showing you my paper. I hate it when I do that. So here. So again, the mass for the sodium chloride was this number right here. The mass for my PbSO4 is that number right there. So it's 303.27. I'll put this over here. And my Mg3PO42, I calculated right here, is 262.87. 262.87 grams per. Now, isn't necessary every time I do this. So you'll see me do this. Every time I write down some formula, I'm going to calculate a molecular weight. Is it necessary? Absolutely not. Sometimes I don't need them. But I always write them because then I know that I'm practicing. And then if I need it, I already have it. So that's one of the first things that you'll see. Now, a percent composition for NaCl, it's going to be the percent Na and a percent Cl. Now, my Na is going to be the mass of the Na divided by the total mass times 100. So what was my mass for the Na again? That was 22.99. So by himself, he's 22.99 grams per mole. I'm going to divide that by the total mass, 58.44 grams per mole, multiply that by 100, and that'll give me my percentage. For chlorine, it's going to be a similar process, but this is 35.45 grams per mole divided by the total mass times 100. So I've set up both of those calculations. And then I can do this on my calculator again, and I'll try and show you the screen for this. I wish I could share my computer like I normally do, but I haven't got that set up on this machine yet. So let me see if I can show you that. Hopefully you can see it. It probably is not visible, not readable, whatever. That gives me 39.34%. 35.45 divided by 58.44 times 100 is then going to be 60.66%. Now, if I do a gut check and I say 39.34 plus 60.66 gives me 100%. So it's just a way for me to double check my work. I can see, okay, did I screw up one of those calculations somewhere, and then I can go look for it? Or am I okay? So that's my one for NaCl. So we'll draw ourselves a line, and we'll talk about PbSO4. Again, we're going to have a Pb. I'm going to have a percent for S, and I'm going to have a percent for O. My Pb is going to be the 207.20 grams per mole, and I know that number is what is on my periodic table. That's all that is. It's me knowing that that's what's on this periodic table. Now remember, I looked up all of those values back here. So 22.99, 35.45, 207.20, sulfur was 32.07. And so I have those written down somewhere. So I don't have to look at my periodic table again. I can just reference those values. We divide the mass of each component. Now, how many PBs are there? There's one. How many S's are there? There's 1. And how many oxygens are there? There are 4. We then divide by the total mass for this PbSO4, which we calculated to be 303.27 grams per mole. Multiply that by 100. That gives me an answer. And let's see what we get here. So we'll start at the beginning, 207.20, divide 303.27, and then multiply that by 100. That gives me 68%, 0.32%, 68.32. We then do the 32.07 divided by 303.27, multiply that by 100. It gives me 10.57%. And 16 divide 303.27 times 100 is 5.28%. Now notice I'm reporting these to two decimal places. Is that really the number that I should be reporting? Well, no, actually it's not. So for this first one, since this is 5 sig figs, I should have 2 in front, 3 decimal places in the back. So that would then be 322. I have 4 sig figs here in the 32.07, so this is an appropriate number of sig figs here. I have 4 sig figs. Oh, oops, this is wrong. And it's wrong because when I punched it into my calculator, all I did was 16 divided by the total times 100. And I can't do that. I have to multiply by 4, then divide it by the total and multiply by 100. And that gives me 21.10%. And if I add all those percentages, 21.10 plus 10.57 plus 68.322, that gives me 99.992%. And that is close enough. If we can get within, I would say 99% or 101% is going to be close enough. Usually you end up with it being, slightly lower than what it should be. So that's what we're talking about there. Okay. So that's within a stone's throw, and I'm not concerned about that. Now we're going to do the same kind of calculation for Mg3PO4-2. So again, I'm going to have an Mg, I'm going to have a phosphorus, and I'm going to have an oxygen. And notice they get smaller every time. Part of that is because I have no paper left. Part of it is because there are bigger things to do. And part of it is because you've already seen me do this in great detail a number of times. So Mg, the mass on the Mg, we looked up. Mass on Mg was 24.31. I need 3 of those because of the stoichiometry in the formula. And I have to divide by the total mass, which is 262.87 grams per mole. And then I need to multiply that by 100. The phosphorus is 32.07. No, that's sulfur. Phosphorus is 30.97. I knew it was something like that. Grams per mole times 2, because there are 2 of them. Once we distribute the 2, 262.87 grams per mole times 100. And then my oxygen is going to be 16.00 times 8 over 262.87 grams per mole. Oh, I didn't write grams per mole. Oh, my Lord. Multiply that by 100, and that'll give me a percentage as well. So first one, 25.31 times 3 divided by 262.81, and then multiply by 100. This is 27.75%. And of course, it's 750, but eventually there are other digits. So we'll leave it as 75 because it's a 0006. So that stays as 5 when I round that. 30.97 times 2 divided by 212.87. I multiply that by 100. And that gives me 29.010. So I need to round the 9 up, and so it becomes 0.10%. And then my oxygen is 16 times 8 divided by 262.81 times 100, which is 48.70%. I can then do 27.75 plus 29.10 plus 48.07, and that gives me 104. I don't think that's a big enough issue for me to go, okay, where did I screw up? I don't think that is. Now, if I were taking a test and I was doing this there, would I do that? Yeah, probably. That's just how neurotic I tend to be. But, at this point, I'm the only crazy person that would do that. So there's no reason for me to walk through and do it again for you guys. If you want to go back and verify it and take a look at it, please be my guest. And if I made a mistake, tell me, and I'll see if I can post a different video correcting that. Okay? So that's how we do our calculations for percents. Now, I'm going to get another piece of paper. I'm going to see if I can minimize this. See if we can do that. Try and make life a little easier. Now, let's see if we can do this. What is the empirical formula of a compound that is 69.94% iron, 69.94% iron, and 30.06% oxygen? Oh, yay, I want an empirical formula. I call that an EF because I don't like to write everything out. So I assume that I have 100 grams total. So 69.94 grams of Fe. I have 30.06 grams of oxygen. And the oxygen is 16.00 grams per mole. Iron, I have to find on my periodic table, 55.85. I need a table I can read better. 55.85 grams per mole. So we do calculate the number of moles, right? So if I calculate the number of moles, I take the mass that I was given, I divide by the molecular weight. Grams cancel. It leaves me with moles of Fe. I will calculate that in just a second. I'm going to set up my second calculation before I do that. That way I can do both of them at the same time. And then 1 mole of O is 16. What the heck am I doing? 16.00 grams per mole. Okay, so I've got two calculations that I'm going to do there. 69.94 divided by 55.85. That gives me 1.252282901. And for now, I'm going to leave that. Now, that is a mole in moles of Fe. For now, I'm going to leave that number. I want all my digits. So 30.06 divided by 16 gives me 1.87875 mole of O. Now we would write this as Fe and then that 1.2522, and I'm going to leave it there, remind myself that that's what I did. And then O, 1.87875. Now I need to figure out what the actual ratio between those two things is. So I divide everything by this lower number. 1.2522, yada, yada, yada. So that's going to give me 1 Fe. But how many oxygens am I going to get out of that? This last number that I calculated, I'm going to divide that by the 1.252282901, and that gives me 1.5. Those are not whole numbers. So that is not going to work. So what we do is we multiply this, Fe2O3, so that we have a whole number ratio. And that is the correct whole number ratio for iron oxide. Okay, so that's what we were talking about there. Now we want to know the molecular formula. I'm looking for an MF. Molecular formula of a compound that has 75.46% carbon, 4.43% hydrogen, 20.10% oxygen. And I'm looking for a molecular formula. Molecular weight, I am told, is 318.31 grams per mole. Okay. So again, I'm going to assume that this is 75.46 grams of carbon. This is 4.43 grams of hydrogen and 20.10 grams of oxygen. Molecular weight of carbon is 12.01 grams per mole. Molecular weight of hydrogen is listed here as 1.01. And oxygen is listed as 16.0 grams per mole. I am going to convert all of those to moles. So 75.46 grams of carbon divided by 12.01 grams of carbon per mole. Leave that for a second. It will do 4.43 grams of hydrogen divided by 2.02 grams. No, sorry, it's not an H2, it's just H. I apologize. So used to doing H2, I didn't even really think about it. And that's grams per mole of H. And then there will be one more calculation that I can kind of sort of squish in here. I have 20.10 grams of oxygen. Divide that by the 16 grams per mole of O. And that'll give me number of moles for that. So I'll take my calculator again. 75.46 divide 12.01. This gives me 6.283. 4 sig figs. So round this up. Now remember, I'm keeping everything on my calculator, but I am rounding this to report on this happy piece of paper that I have. 4.43 divided by 1.01 will give me 4.34 mole of hydrogen, 3 sig figs, because both of those numbers are only 3 sig figs. And then 20.10 divided by 16, which is 1.25625. And again, process is, then I write carbon 6.284, hydrogen 4.34, oxygen 1.25. I will divide them all by the oxygen, because that's the lowest number. So I'll end up with carbon, a hydrogen, and an O, which is 1. So I explicitly wrote the 1 here. It's just a reminder to me that I actually did that math. 4.34 86138614 divided by 1.25625, and that gives me 3.5. And if I do the carbon one, that's 6.28309 28309. Back and forth and back and forth. I should have stored things. 74.19, 7419. I will divide that by the 1.25625, and that gives me 5. Now, these are not whole numbers. Again, that hydrogen is causing me an issue. So if I multiply this by 2, I get C10H7O2. Now, that's my empirical formula. So what is the mass of that empirical formula? And I'm actually going to do some funky things. I have the luxury of having electronic paper so that I can move things and make more space for myself. I cheat, I know. And I erase too, which I never used to do. I always wrote everything in pen because that's the expectation, is that chemists always use pen. I was taught to use blue pen because then if I make a photocopy of it, I can tell the difference between the original. You get the point. But I never used a pencil. I used a pen, and if I made a mistake, I would single line through it, initial it, and date it. And usually when I date it, I go 0608, because then it's completely clear what I'm talking about. Although, depending on which company I was working for, sometimes it was in a different format. But that's besides the point. My point is, I want to know what the molecular weight of this empirical formula is. So I take 12.01, which is the carbon, and I multiply that by 10. I add to that 7 times the 1.01, which is the hydrogen, plus, just a second, sorry, I'm grouping some things. Times 7 plus 2 times 16 . Calculator issues, I apologize. Give me just a second. You can fast forward. I can't. I get 159.17. Now, they told me that the molecular weight was listed as 318, so that's not consistent with what I see here. I can take that 318.31 and I can divide that by 159.17. So I take the overall mass for the molecule, I divide it by the mass for the empirical formula. That gives me 1.9998, which is 2. So I know that I need to take and multiply this by 2 to get that right answer, which then means that this is C20H14O4. So I've had to multiply everything by 2 to get the correct molecular formula. Okay, so now we've got examples of all of this stuff that we talked about last time when we talked about converting to moles, converting to molecules, then doing percent composition, and then going from percent composition to empirical formula, and then to molecular formula. All right, so that's our review from last time. Go, awesome review, yay! Let us continue forward. I'm going to put this, hopefully, back up. I'm not going to do the whole presentation thing. You can look at the slides by themselves if you really want to. I'm going to leave it like this for now because then I can flip to other things if I need to. We're going to talk about chemical reactions and chemical equations. Okay, and you study chemistry to learn how one atom or molecule is chemically changed into another substance. So how do we rearrange those molecules? Because that's really all we talk about in chemistry, is how do we rearrange those molecules so that we get from one thing to another thing? And it has to happen in particular ways. All right, so that's what we're going to be dealing with these kinds of chemical reactions. Now, when we get to the nuclear reactions, we're going to be converting particles from one type to another type. That's a little bit different. That's nuclear chemistry. But in general chemistry, we do not create or destroy mass. We do not convert things in terms of going from one type of atom to another type of atom. We're just going to rearrange the atoms that we have. So for example, we have H2 gas plus O2 gas going to H2O gas. Okay. Hydrogen gas reacts with oxygen gas to yield steam, gaseous water. But do we have the right number of things here? And the answer is no, because it's not balanced. I have 2 oxygens on the reactant side, but only 1 on the product side. And so that means that I need to do some fixing. So the first thing I would do, if I were doing this myself, and I'm going to move this so I can show you my thought process here. It's one of the weird things about not being in a physical class. I have to show you what I would typically draw on the board. So I start with H2 gas plus O2 gas going to H2O gas. And I know that I don't have the right number of oxygens over here, so I'm going to multiply this by 2. Then I see, oh, garbage. I fixed the O, but now I've screwed up the H. So I have 4 H's on this side and only 2 on this side. So I can multiply that by 2. And that again gives me a balanced equation. Now you'll see me do this. I'll write down H, O, and then you'll see me do on this side of it, on the left side, that's what's on my reactant side. And on the right side, that's in my products. So I have 4 H's over here. I have 2 oxygens over here. I have 4 H's over there and 2 oxygens over there. And since everything is matching up, then it's balanced. Go balanced. Awesome. We love that. So that's what we were looking for. We now have everybody the way we're supposed to, and we're good. Yay! We're good. So let's see what happens next. The reactants are the starting materials for your chemical reaction. Product of the substance is formed as a result of the chemical reaction. So we go from reactants to products. We like to include the physical states of these things. We do this whenever we can because eventually we absolutely need them. So when you get to the second half of this class, you start talking about chemical equilibrium, we only include certain phases in those calculations. So it's important that we indicate those phases when we talk about this. So if you don't know what they are, you don't know what they are. So you don't have to include them. I usually tell you what they are on the test. Oh, so you made gaseous water. Hint, hint. You should include that. All right. So 2CO gas plus O2 gas goes to 2CO2. And of course, we have 2 carbons on the reactant side, 2 carbons on the product side. I have 4 oxygens on the reactant side and 4 oxygens on the product side. So that is balanced. When we indicate the physical states, there are several new designations that we need. So G is gas. We've talked about the gas part for that. L is for liquid. So that's a pure liquid. So if we have water and there's something dissolved in it, that is not a liquid. Okay. We may, if we're talking about the dissolution process, we'll list it as a liquid because we haven't gotten the equilibrium to get everything in solution yet. So S is for solid, and AQ are for materials dissolved in water. It means aqueous. So that's what we talk about there. Now, you'll see NaCl going into H2O goes to NaClAQ. So while the water is explicitly shown here, we don't always do that. We don't always write out that step happened. We just assume that you know if I write NaClAQ, that you know that that's what happened. Okay, so I have to do that. So it's something that we assume that you know, and we usually omit. But that is the process that goes on there. Okay, so if you take a solid and you put it into water, that is what you do or what you should show, and it should come out as AQ. What it does from there depends on what it is, and we will get to that eventually. Balancing chemical equations. We need to identify all reactants and products and write the correct formulas on the left or right side of the arrow, respectively. You cannot balance an equation by changing the formula of a compound. So remember, we have talked about how we write these formulas. We have talked about, oh, sorry, you need to see my paper again. We've talked about how we write these formulas. We've talked about the way that has to be the way that it is. So we can't change those subscripts here. Those subscripts are determined by the chemistry that goes on. So it's an ionic compound. We have the number of cations, the number of anions demanded by the charge on those two species. In a molecular compound, we will eventually talk about why we make the bonds that we make. So it's not possible to just say, well, okay, I don't like that number, so I'm going to change this H2O to H2O2. That's a completely different compound. We cannot do that. So the only way that we can balance is by putting numbers out in the front. All right. So the thing in the front is the only thing that you can use to balance. The things that are in the equations with the subscripts, those are fixed based on the reaction that you're doing. Okay. So that's what we have. So if I tell you that I'm reacting KClO3 going to KCl plus 3O2, while I know that that's not balanced, I cannot change those subscripts. All right. So one of the ways that you'll see this is that we'll tell you, the name of this particular compound reacts with the name of so water reacts with sodium chloride to give me sodium chloride in water. So aqueous sodium chloride. So then I would know that I took solid sodium chloride, I added that to liquid water, and that gave me aqueous sodium chloride. Okay? So that's why the names become important. We need to make sure that you know exactly what we're talking about. Often you'll be told what the phase is, especially for me, so that you can put that phase in the equation. Points will get deducted if I give you all of the phases and you don't include them in your balanced equation, because that's a habit you need to get into now. One of the things that I found as a student was in the first half, I didn't bother to write down the phases. Why? I didn't need them. What was the point? And so then I got to the second half and I realized that I did need them, and then I had to retrain myself how to write the damn equations. It's a pain in the neck. So start doing it the right way, and then you can worry about that later. Okay. Now, I want it, if I'm going to balance something, I want to balance anything that's not H or O first. So if we're talking about a reaction like KClO3 will give us KCl and oxygen gas. So something like this, KClO3 solid. And we heat that up, and I'm going to write it, and don't worry about it. All this delta means is that I heated it. You don't have to do that, but my head will explode if I don't. So that gives me KCl solid plus an O2 gas. All right. And now that I have established what my formulas are, now I have to see if this is balanced. So I have one potassium. So I can write my potassium, my chlorine, and my oxygen. One potassium, one potassium. One chlorine, one chlorine. 3 oxygens, 2 oxygens. Oh, we not happy. We not happy. Okay, fine. So this is 3, this is 2. I can't multiply this by 2 to get that. So I'm going to have to multiply this one by 2, which will give me 6 oxygens. And then this one, should have left myself space, by 3, which will give me 6. So now I have the same number of oxygens on both sides. However, when I did that, I screwed up the K and the Cl. So now I have 2 Ks and 2 Cls, which means I need to go 2 over here to get me 2 and 2. So what did you see? Oh, garbage. Hopefully you understood what I was doing there. So I wrote down my K, I wrote down my Cl, and I wrote down my O. I wrote in this first column that you'll see here, this first column right here, that's indicating what I had to start with. This indicates what I had to start with. When I see that these two aren't the same, so I have a 3 and a 2, I need to look for the lowest common denominator between the two of those. So I multiplied this side by 2 to get a total of 6. And I put the 2 out here, because I need to put the 2 out in front of this if I'm going to do that. Then I put a 2 out in front, or a 3 out in front of the O2, because then I will get 6 oxygens on the product side. So now my oxygens are good. I fixed the oxygen problem by doing that. But then I also screwed up other things. So on the product side, the only thing I changed was the oxygen. On the reactant side, I changed potassium and chlorine as well. So that's why I crossed out the 1 and wrote a 2 for both of those, because I multiplied that by 2 so that's what I now have is 2 Ks and 2 Cls. So that's what I now have. If that's the case, then I need to multiply something on the other side to get 2 Ks and 2 Cls. Turns out that the K and the Cl are together, so I can multiply that by 2, and then that means I go from 1 and 1 here to 2 and 2 here. All right, so that's what I was doing. Now, again, do you need to do it that way? Absolutely not. Is this the way that I do it? Yeah, absolutely it is. And one of the things that I used to do as a student was every time that I wrote something, I'd leave myself a little gap and I'd write the first number. If I then had to change that number, I would cross it out, write a different number above it, and then initial and date it. For an example. Again, is it necessary to do that? No, of course it's not. As long as you can follow what you did, it's not a big deal. But I took the opinion that I want to see whatever I did, because if I screwed up somewhere and I could follow the thought process I used to get from point A to point B, I could find the flaw in the process. And so for me, that was helpful. It is not required that you do it. Nobody's going to mark you off if you don't. Okay? So that's what we're talking about with that one. All right. I hope that makes sense, because I know you couldn't see what I was writing, and I apologize. So Now we've got that. And here I talk about, okay, I did this, I screwed this up, I have to fix things. And that's exactly what we were talking about. So I'm going to move this back. And again, I don't feel entirely guilty about doing this because you have copies of the slides that you can look at so that you can see them when they're bigger. So that's our balance. That way I won't forget to show you the paper anymore. So that's our general process for balance. Okay. What's our next topic? Where are we going next? Oh, create a balance sheet. And this is exactly what I was talking about with that balance sheet. So that thing underneath my equation that I do here. Come on. Show me. There you go. So this is my balance sheet that I write down. Okay. And again, it's just a way for me to keep track of what the heck is going on. So do I need to balance it the way that I've balanced it? Well, it is balanced, but it doesn't have to be that. So let me show you an example of what the heck I'm talking. So we talked about this equation here, 2H2 going to O2 plus 2H2O. That initially was H2 gas plus an O2 gas going to 2H2O. And if I look at my initial table, I have an H and an O. I have two H's and two O's. I have four H's and two O's. That's not what I thought I needed to do. Bummer. That one's not going to work, and that's not going to help me. let me see if I put one in here, because hopefully I did. I think that I did. Let's go ahead and practice these, and if not, I will find one and come back to it. I apologize. I'm all over the place today. So nitrogen and hydrogen. Nitrogen. And this is when we need to start talking about those things. Hydrogen, these are both gases. To give me ammonia. I'm going to make that a gas because I know I can do that reaction in the gas phase. Now, we talked about this before. We talked about the fact that there are 7 things that always occur as diatomic molecules. And periodic table. See this. So if we refer to this table right here, this one that we've got, I know that a hydrogen is always diatomic. So he's this top corner right here. The rest of them on the table form what I like to call the 7. So there are actually 7 of these. 1, 2, 3, 4, 5, 6. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are 6. And then H2. So those guys that make this funny little 7, and then hydrogen. So those are the ones that always appear as diatomic gases when they're by themselves. That's how they appear. We'll get to why someday. All right, but this is what we have. So this is my equation. Let me write my balance sheet. I have 2 nitrogens there. I have 1 there. I have 2 hydrogens there. I have 3 there. The only way I'm going to be able to make the hydrogens work is if this is a 3 and this is a 2 for a total of 6. Yeah, I want my total. If I change this to 3, that gives me 6. If I change this to 2, that gives me 6. And now I have 2 nitrogens. So that is a balanced equation. Oh, yes, awesome. I can talk about the decomposition of H2O to give hydrogen, again diatomic, plus oxygen, diatomic. So I have H2O. I have an H, I have an O. I have 2 H's and 2 H's, 1 O, 2 O's. How am I going to fix that? Well, I have a couple of options. So I can multiply this thing right here by 2, which is the way that we've done it before. If I leave it by itself, and I put a 1/2 out in front of that, then instead of having 2, I only have 1. Now, what did I do there? I knew that oxygen was screwing me up. And so since O2 is always O2, I can take fractions of O2 to give me single numbers of O2. Okay, so that's what we talk about when we say we can use fractions to do this. So it's either the 1/2 here or 2H2O goes to 2H2 plus 1O2. At this point, there is no reason that one is more acceptable than the other. It's our preference to use not fractions, to use whole numbers, just because it's more aesthetically pleasing, but that's all it is. It's just a convention. Okay. So questions, comments, problems on that? I hope not. That will take us through balancing those two. Now, methane and oxygen. Methane, I believe, is CH4. Let me check my notes. Yes, go me. So that is something that I had to look up. You saw me do it. So that would be in that table that I gave you on the test, the common names. See, methane would be in there. So methane plus oxygen react to give carbon dioxide and H2O. Hydrogen, carbon, oxygen. So carbon is first. I have 1 carbon and 1 carbon. I have 4 hydrogen and 2 hydrogen. I have 2 oxygen and 3 oxygen. Now, since this one's not right, the hydrogens, I'm going to make this be 2. That means I then have the right number of hydrogens. Now I have 4 hydrogens. And I now have 2 oxygens on that. The 2 from there and the 2 from there then give me 4. Since I have 1O2 over here, I can multiply that by 2, and that gives me 4. So, awesome. Awesome possum. We are in a good place. Hopefully that makes sense to you guys. So my process is, what is the balanced equation? What are the formulas that I need to have in this? Let's make sure that all of our formulas are right. Reactants, products. Then I go to balancing, and that's where this table comes in to help me make sure that I've got everything balanced between reactants and products. Reactants and products. All right, so that is my process there. Now that took us through the methane. Let's go to the next page, and we'll talk about ethane. So it says that ethane, C2H6, reacts with oxygen, and that gives me H2O plus CO2. Oh, Lord, that looks a lot like the other one. And that is correct. So what you're looking at here is actually a combustion reaction. So if we take it and we add heat to one of these things in the presence of oxygen, it breaks down into carbon dioxide and water. That's a combustion reaction. We see those all the time. And alkanes are very good at doing that kind of chemistry. Okay, well, we then have carbon, hydrogen, oxygen again. I have 2 carbon here, I have 1 there. I have 6 hydrogen here, I have 2 there. I have 2 oxygens here and 3 there. Now let's fix our carbons first. So I'm going to multiply this by 2 because that makes 2 on each side. Awesome. When I do that, I then screwed up the O's. So I now have 5O, and I still have 2 on the other side. We'll get back to that. Let's talk about our hydrogen. I have 6 on the reactant side, and I have 2 on my product side. So if I multiply this by 3, then that fixes that. And I now have 7 oxygens. Ooh, I know it's oxygen. I have 7 of them. And I have 2 on this side. Oh, Lord. That damn thing. So this is another place that I can do funky math. I can go 7 halves. So I could do it that way. And that then means that I'm going to have 7 over here. If I wanted to do it so that all of them were whole numbers, I could do 2 of those, 7 of those, because if I multiply that by 2, that's just going to leave me 7. Instead of 3 here, I'm going to have 6 here. Instead of 2 here, I'm going to have 4 here. So looking at what I have, that then gives me 4 carbons, 12 hydrogens, and 7 oxygens. Put the 12 in the wrong place. And then, as written, I have 4 carbons. Go awesome. I have 12 hydrogens. Go awesome. And I have 6. Those are not even. All right, give me a second. I'm going to start over because I have confused the heck out of myself. I love it when I do that. Okay. C2H6 plus O2 goes to CO2 and H2O. Carbon, hydrogen, oxygen. 2 carbons there, 1 carbon there. 6 hydrogens there, 2 there. 2 oxygens there, 2, 3 on this side. Oxygens are screwed up. So I'm going to multiply this one by 2. That gives me 2, 3, 4 on that side. To get 4 back on this side, I multiply this by 2. I now have 4 on both sides. I also have changed the number of hydrogens that I have over here. So instead of the 2, I now have 4. Oh, Lord. Okay. Still have 6 on this side. And my carbons are messed up. So let's try multiplying this, which then gives me 2 of those. It also changes my oxygen. So now I have 2 from there. Sorry, 2, 4 from there, plus 6. 6. I can then change this to 3. That gives me 6. So 2 carbons, 2 carbons, 2 carbons, 2 carbons. I have 6 hydrogen. I have 2, 4 hydrogen. Oh, that did not work because I'm still messed up with my hydrogen. Lowest common denominator, I can multiply this by 3. That means I then have 3 plus the 4 is 7 hydrogen. And this one stays by itself. So now I have 7 hydrogen, 3 oxygen, 6 hydrogen, and 7 oxygen. So now I've got 2 carbons, 6 hydrogen, and 6 hydrogen. I have 2 times 3 is 6 oxygen on this side and 7 on this side. So I have 4 there and 3 there. And that's not balanced. If I were to thinking. It happens. Oh, went somewhere I wasn't supposed to go. I'm going to try doubling this. Let's see what happens if I do that. So that gives me, then I have 4. Haven't done that side yet. That then gives me 12. Let's do a 6 here. 602 gives me 12 total. I now have 4 of these. 8 oxygens. Oh, and I need to multiply this by 2. So I now have 8 and 6 are 14 hydrogens, which is no longer balanced. This is one of the ones that when I was a student I would have killed myself over. All right. Well, I got myself into such a tizzy I couldn't think, so I got up and walked away and stepped away for a little bit. So we're talking about C2H6 plus O2 going to CO2 plus H2O. We have our normal C, H, and O. I have 2 carbons. I have 6 hydrogens. I have 2 oxygens. I have 1 carbon. I have 2 hydrogens, and then I have 3 oxygens. Okay. I'm going to fix the carbons first. It's the most pressing and immediate thing that I need to do. So I'm going to multiply this by 2. That then gives me the 2 there. I then end up with 4 oxygens from this and 1 from there, so that's 5. Okay, fine. Hydrogens. I have 6 on this side and 2 on this side, so I'm going to multiply this by 3. That then gives me 6 and 6. So carbon and hydrogen are both happy. I have changed the number of oxygen. So I now have 4 from carbon dioxide and 3 from H2O, which is 7. And I'm pretty sure that I got to this point before. And I said, oh, there are 7 on this side and there are 2 over here. So if I multiply this by 7 over 2, then that leaves me with 7. So that is balanced. Now, not everybody likes it this way. So sometimes what happens is people will multiply this by 2, which then leaves me with four there, 6 here. And of course, that leaves me with 7 right there on the O2. And if I do another gut check, I have 2 carbons on this side, and I have 12 hydrogens. So, no, not 2. There's 4. I can do math. 4 carbons on that side, 12 hydrogens on that side, and 14 oxygens. I have 4 carbons. I have 12 hydrogens, and then I have 8 plus 6 is 14 oxygens. Oh my god, I can do math, and that worked. So that is the balancing for that. Now, 7 halves is fine, i.e. C2H6 plus 7 halves O2 goes to 2 CO2 plus 3 H2O. Either one of those at this point will work for you. There's no particular reason that you need to do one over the other. Right? Later, that will matter, but it's entirely up to you which you're more comfortable with. I really don't care. So in grading, it's not going to matter to me. Now let's talk about PCl5. Is that 3? Now I do know that people are. I know that some people are going to complain that I didn't turn it off. That I made you watch me do what I did. Part of the reason that I do that is because I need you guys to see that I struggle too. You know, there is nothing wrong with struggling with this, and sometimes the only way to figure it out, quite honestly, is to Google it and make sure that you're not crazy, and that's okay. It's important that you do the practice. It is my hope that you never get an ugly question like that on a test. Now, that doesn't mean it doesn't happen. Sometimes I'll ask just to see if you give me a fraction, but it is my hope that that does not happen. Now, if I give you a question that nobody gets right, then that gets curved out. So we take those points out. So please don't worry about that. Okay. Let's see what we can do here. PCl5. So I've got a P, got a Cl, got an H, I've got an O. I currently have 1 P, 5 Cls, 2 H's, and 1 O. I have 1 P, I have 4 Cl, I have 1 H, and 1 O. Well, I was happy, so that's awesome. But we're going to mess things up. I absolutely know it. So I don't have enough H on that side. But I also know that I don't have enough chlorines on that side. I'm going to multiply this by 2 to fix the H. That means that I then have 2, 5. Awesome. So I fixed both of them. So I have 1 phosphorus. I have 5 chlorines. So 2 from there, 3 from there. 2 hydrogens. 2 hydrogens. 1 oxygen. 1 oxygen. I'm balanced. Go. Go us. Did it the first time. See, some of these are easier. SC2O2 plus SO3 checking something. Give me a second, because I'm suddenly remembering there was one of these that wasn't balanced the way that it wasn't written the way that it was supposed to be. I'm wondering if it's this one. Because that's what's written on my slide. Well, let's try this. S, C, S, and O. So I have 2 SC over here, 2 on that side. Woo! I have 1 sulfur and 3 sulfurs. I have 6 oxygen at the moment, and 12 over here. So I need to multiply this by 3. If I multiply this by 3, so the SO3 by 3, then that changes the S to 3. So scandium is good, S is now good. I have changed that to 9 plus 3 is 12. So, woohoo! That one's balanced too. Al plus H2SO4, Al2SO4, 3 plus H2. AlSHO. So I have 1 here, 2 here, 1 here, 3 there, 2 there, 2 there, and then oxygen, I have 4 on that side, and 12 on that side. Okay, so sulfur is the thing. So let's fix the Al. That's an easy fix. We'll multiply that by 2, and then Al is happy as it is. We have 3 sulfur on this side. I only have 1 on this side, so I'm going to multiply this by 3. Now that gives me 3 S's. We now changed the number of hydrogens, so I now have 6 hydrogens. And then 3 times 4 is 12 oxygen. Okay, so oxygen is balanced, aluminum is balanced, sulfur is balanced. Hydrogen is not. So since hydrogen is only 2 here, I can put a 3 in front of that, and that then gives me 6. Yay, I balanced stuff. Awesome. Now, is this going to take you forever? It shouldn't. It really shouldn't. It's going to need to be practice. So that is the expectation there, is that there's going to need to be practice. I hope that there are no questions, comments, problems. Bear with me just a moment. I apologize. I'm so sorry about that. I've been trying to make an appointment. Somebody finally called me back. Yay! All right, so that's the balancing equations. Again, it's going to be something that you need to practice with, but it should not be that bad, okay? There are only some of them that become that bad, and for some reason, for me, it's always the hydrocarbons that become that bad. So hopefully there are no questions, comments, problems. If there are, please let me know. You know I'm good with taking those questions, comments, problems. Now I'm going to try and get this into screen sharing mode again. See if it will let me. No, I'm sharing there. That's not what I want. I want this. I hate it when I get these windows like this. Slideshow from current slide. Okay. So now we're going to talk about nuclear reactions. So we've talked about standard chemical reactions. Now we're going to talk about nuclear reactions. So all elements having an atomic number greater than 83 are radioactive. They emit particles or electromagnetic radiation spontaneously. That's called radioactive decay. Nuclear transmutations occur when nuclei are bombarded by neutrons, protons, or other nuclei. So if it happens spontaneously, that's a radioactive decay. If it's something that we have to induce by hitting something with either with a subatomic particle, another nucleus, some other atom, then that's what we call nuclear transmutation. Okay. In chemical reactions, we talk about atoms being rearranged by breaking and forming of chemical bonds. In chemical reactions, only electrons in atomic and molecular orbitals are involved in the breaking and forming of bonds. So it's just the movement of the electrons. So we either move them completely from one species to another, or we rearrange them. Okay. Reactions are accompanied by absorption or release of relatively small amounts of energy, which we don't really talk about until the next class, so in 111. And then rates of reaction are influenced by temperature, pressure, concentration, and catalysis. And again, we don't talk about kinetics until 111. So there's that. That is everything for chemical reactions. On the nuclear reaction side, elements or isotopes of the same element are converted from one to another. So I can take an element and convert it from one thing to another thing, or I can take one isotope and convert it to a different isotope of the same thing, or something else. Protons, neutrons, electrons, and other elementary particles may be involved. So it could be a number of those things, depending on what is happening there, whether it's spontaneous or what we're trying to do. Reactions are accompanied by absorption or release of tremendous amounts of energy. This is part of the reason that nuclear reactors are used to generate energy. So that's something that we see around us. Rates of reactions normally are not affected by temperature, pressure, and catalysis. So the things that typically work in a chemical reaction aren't going to work in a nuclear reaction. They are very different. They're two very different processes. Okay. You may get a question that says, look at this reaction. Is it a chemical or nuclear reaction? Or what type of reaction is this? Right? So that's something that you may see. That's one of the things that we'll do with the nuclear. I'm going to go ahead and go to the next slide. You will need to be able to write out the symbol given the name. So if I give you an alpha particle, if I say, what is an alpha particle? You need to be able to tell me that it's a 42He. A beta particle is then so beta particle, again, is going to be this 1E. Okay. So remember, we're talking about mass number at the top, atomic number at the bottom. So this is no different than what we've talked about before. When we talk about isotopes, this is the same kind of thing that we're looking at here. Okay. Positron is effectively a positively charged nucleate or electron, sorry. And proton, we know what that is. That's a 11H. Okay, we can also list that as a 11P. We can have neutron, which is a 10N. We also sometimes see gamma rays. So if you are familiar with the Hulk, that's what he was bombarded with. However, it does not normally turn us into the Hulk. Bummer, because I always wanted it to be the Hulk. But you need to know how to write me one of these particles or how to identify those particles. So you'll need to know this table. This table, I think that I provided this in the exam handouts. Let me verify that because I have that over here. I apologize. Did I give it to you or apparently I did not. So you will need to know this table. And again, that's just so I can ask you about it. So you will need to know that. One of the reasons for that is that you will get balancing equations. And the same way that we expect that you can go from the name of something to balance an equation, we're going to expect that you can go from the name of something to balancing a nuclear reaction, and therefore you need to know what those particles are. Now let's take a look at the balancing that goes on here. So I have a 2512 Mg plus a 42He, which, remember, we just saw that that's an alpha particle. So I have bombarded this Mg nucleus with an alpha particle. I then get a proton out of it and something else. So this something else, I don't know what it is. I know it has a mass number, and that's going to be the A value at the top. I know it has an atomic number, and that it's not going to be the same as what I had before. And whatever that atomic number is going to determine what the symbol is, okay? So the sum of the mass numbers on the reactant side is going to be the same as the sum of the mass numbers on the product side. So I have a 2512 Mg plus 42 He. So let me write this down, and then I'll show you my paper. And that goes to this 11H plus this AZX. Paper's back. So AZX. All right. And I know that these top numbers, the sum of the top numbers on this side has to be the same as the sum of the top numbers on this side. So if I have a 25 plus 4, it gives me 29. I then subtract the 1 that's over here already. That gives me 28. That means that this AZ, A is 28. So I've dealt with my mass number. I can then talk about the number of protons, i.e. the protons in this. I have 12 plus 2, which gives me 14. I can then subtract the 1 from this side, and that gives me 13. So my Z is 13. All right, taking the sum on the reactant side, subtracting out what I already have on my product side. So that gives me 13. So now I look at my periodic table and I go, okay, who's 13? 13 is aluminum. So X equals Al. And so my answer would be written as Al 2813. Now, for those of you who are in online classes, this is either going to be one of those ones where I'll expect you to turn in your paperwork to show me that, or I will specifically ask you on the question, how many protons, how many neutrons, how many electrons are we dealing with in this product? You know, what would be the mass number of this? What would be the atomic number of this? What would be the symbol of this? Because I can ask both of those questions. And I may do one or the other or both. It depends on how much manual grading I want to do, or how much I want to put in to let it grade for me. So I haven't figured that out yet, what that balance is going to be at this point. All right. So that's how we deal with balancing the nuclear reactions. Now, I know that there's another one over here, and I have 21498PO. So 214, and that's not 98, that's 84. 84 PO plus 242HE is going to, plus 2 electrons is then going to give me 22286Rn. And I want to check this. So 214 plus 8 plus 0 is 222. 84 plus 4 minus 2. 88 minus 2 is 86. Okay, so remember that when we're dealing with these negative particles, these guys right in here, these negative particles, we are then going to be talking about subtracting that out. So this is going to be the same kind of math that we typically do. Don't forget the negative on that calculation. Okay, so that is a verification that that is a balanced equation. All right. Questions, comments, problems on the balancing of nuclear? Hopefully not. To me, this is extremely straightforward as long as you know what the particles are. So again, that set of particles is going to be important to you. And that's that one right there. So the set of particles, knowing what they are, being able to identify them and write them out, is then going to make it so that you can do the balancing of this. Now, let's be realistic. How much of this are you going to see? Some, maybe 2 questions. So do you want those points or do you not? Is it worth it to you to study all of this to get those points? That's a question I can't answer. I know that I would, but that doesn't mean that you're going to. And so I just like to be honest with my students about what it is that they're talking about. Okay. So some more balancing examples. It says that NASA uses the alpha decay of plutonium-238 as a heat source on spacecraft. We want to write that equation. So alpha decay, and alpha is a 4,2-He. All right, and it's a decay, so that means that my reactants are going to give me a product of 4,2-He. And I do this from plutonium-238 to 38 plutonium, which is Pu. Plutonium, once I find him on my periodic table, and he's down near the bottom because he's radioactive. So he's going to be down near the bottom. That's polonium, active plutonium. I love it when I can't find stuff. I even know which symbol it is. And I still can't find it. Yeah, there we go. Pu 244. He's 994. Which I have written on the slide already, and you're probably going, why don't you just use it? Because I need to do it the way that I would do it if I was doing it on a test. So I need to show you what it is that I'm doing. So I find it on the periodic table. That tells me what its atomic number is and what its symbol is, because all I really knew was that it's plutonium, didn't necessarily know its symbol, and that becomes this right here. So 23894 Pu gives me this 4,2-He, and then I'm left with other stuff, right? So we have an AZX situation again. Question comes, what is that AZX? So we have 238 minus 4, which is 234. So that's my A. I have 94 minus 2. That's my Z. And that's 92. So if it's 92, then I need to come back from plutonium, which is right there, to uranium. So 92 is U. So that's going to be a U 2, 3, 4, 9, 2. So that's my bar. Okay. And of course, if we put that back into the overall equation, that's what you see on the last thing on that slide. Okay. Questions, comments, problems on that? So now we're going to do some practice in the balancing. So beta decay in BK249, positron emission in O15, an electron capture in I11, or 111, sorry. So it's BK 249, and we get out of beta. And if I go look at my slides, because I can't remember, and at this point you don't know yet, so these are the slides that we need to look at. My beta is listed right here, and it's a 0E. Zero, 1, E. So it's a positive electron. That's my beta particle. And it's a decay, so that comes off on that side. I'm going to have to talk about what the other product is. So this is going to be an AZX. So positron emission in O15, that's an O15. If I want to go back to this slide right here, what's a positron? That's a 0 plus 1E. So it's exactly the same as the beta particle. Plus an AZX. Notice I haven't filled in these numbers yet because I don't have them at the moment. So we'll talk about that in a second. And then I have electron capture in I111. My electron is going to be a beta particle. So 0, 1E. Okay, awesome. Electron capture, so he's a reactant. Cool. Now, BK is number 97. 97. Oxygen is number 8. And iodine is number 53. So if I look at this, I have my 249 minus 0, that's my A. So the A should be 249. My Z is going to be 96. So I take the 97 minus 1, that gives me 96. If I look on my table for 96, that's CM. Okay. I think there's a typo on that slide. I think it should be a negative on the E. So the beta particle, I think, should be negative. 0, negative 1E. Because that would then make this 97 plus 1, which is 98. Is CF. And the reason that I think that it should be like that is because that's actually more stable than what I had written the first time, which you don't know, but that's okay. I think that this is the correct symbol for this and not the 0, 1 electron. I think it should be a negative down there. So I'll have to verify that and update that table for you. I have a 1580, and it does positron emission, so 0 plus 1E. And then I have this AZX. So 15 stays 15. 8 minus 1 is 7. 7 is nitrogen. And then I have the electron being added to the 111. We're bombarding this with an electron. which then gives me a product. So 0 plus 111 is 111. 1 plus 53 is 54. 54 is XE. And again, that should be negative. What the heck? It's not 54. That's going to be 52. And that means it's not XE. It's going to be TE. Yeah, that beta particle has got to be wrong. It has got to be a negative number on that one. So this one right here. So I will make that change on the slides and repost them just so you guys have that available. There's a reason that you should see it like that. Let me take a pause here so I can fix it. Okay, I will get that posted. I apologize for that. This is part of the reason that I steal images from places, because I assume that the images are correct and that I can't screw things up. But apparently I stole something from somewhere that is not correct, because I have compared it to other things that are out there and everything else says that that's negative, which makes more sense to me. Okay. Questions, comments, problems? I hope not. Let's just make sure that we get those particles right. And if you do, then you should be good with everything you're doing for balancing equations. And this took way longer than it should have because I kept losing the plot. And unfortunately, that's going to be something that happens to you when you're trying to do this from time to time. Again, on tests, I try to minimize that, try to make it so it's not that complicated, i.e., I don't want you spending the entire test trying to balance an equation. So I wouldn't worry about that too much because I'm very aware of what that does to somebody. So there's that. I would practice. And again, my recommendation to you is to take the exam handouts and use those whenever you're practicing. So with Alex, I would use them there because that'll tell you what you're expected to know and what you're not. So if it's in there, you don't need to know it. If it's not in there, then you need to know it. And that's something that you need to put down to study. Now, the other thing is it's going to familiarize you with what's where on those handouts. So it'll make it easier for you during a test to use them. Okay? So hopefully that's good to go for everything here. I apologize for this taking forever. And yes, I could have recorded it again, but you know what? No, you need to see the struggle is real. So thank you for bearing with me today. I do appreciate it. I will get this posted and make the change to those slides for you. And I will see you next time. Thanks.